Okay, so here's where we left off in class today. So we talked about classifying discontinuities. And the next page in our notes, it has some things that are pretty subtle, I think, and hopefully I'm able to make this clear for you. Okay, so we're going to start with talking about one-sided continuity, and that we can call a function, it can be left continuous or right continuous at some number, as long as the limit from the left is equal to that function at that point. Okay, so let me explain, like, what the heck does this mean? Okay, on the one that we did in class, I could say that this is continuous here, and we just called it continuous. But technically, we're going to say it's left-hand continuous at that point, because the limit as we come from the left of 9 is equal to f of 9. Okay, so I say it's continuous, but I really mean it's left-hand continuous. Okay, over here, this one is not right-hand continuous, because as I'm headed towards 9 from the right, the limit is going towards, let me see if I can see, -7. But f of 9 does not equal -7. So this does not have a right-hand continuity. Okay, so, and these you kind of have to think about because they're very subtle. Okay, so that's how we can be left continuous at a point or right continuous at a point. And we reserve these for endpoints of an interval that we're looking at. Okay, this just talks about what we just said, that something's continuous at a point if the limit at that point, and remember the limit, you have to check the left and the right, but if the limit at that point equals the function at that point. Okay, now we're going to talk about something very, very subtle. And we're going to talk about if it's continuous on an open interval or if it's continuous on a closed interval and what the difference means. Okay, so when they're talking about an open interval, they're just saying that we don't include the endpoints. We have parentheses here. Okay, and if it's continuous at each point in the interval. So this is telling you don't include A and B. Okay, well, there we go. So this is a function that is continuous on the interval from A to B. I don't care what's happening at the endpoints, but at every point in between, it's continuous. Okay, so now if it's continuous on a closed interval, okay, so now we have brackets. We're saying include those endpoints. They're saying, well, it'll be continuous with brackets as long as it was continuous on the open interval, and the function is continuous from the right at A and continuous from the left at B. Okay, what the heck does that mean? Okay, so here we have a function that is continuous on the closed interval AB. So it's continuous everywhere inside the interval, and it's continuous from the left at B, and it's continuous from the right at A. Okay, and you can think f of A is equal to the limit as it's coming to A from the right, so I know that it's right-hand continuous. On this one, f of A does not equal the limit as this is coming towards A from the right, so it is not right-hand continuous. Okay, so that's what that means. Okay, now another thing that we're going to see is that proving that something's continuous is kind of a drag, and we're going to be doing a lot of problems that we have to have guaranteed that the function's continuous. So if there's some things that we know ahead of time, then we don't have to prove it. Okay, so the first one that they're telling us here is that all polynomials are continuous over all the reals. Okay, so polynomials look something like this. So we don't have to prove it. If we know we have a polynomial function, we can just state when they say, okay, make sure that your function's continuous, and you can say, well, it's a polynomial. I know it's continuous over all reals. I don't have to prove anything. Okay, if it's a rational function, remember the kind with a fraction in it, they're saying it's continuous on its domain. Okay, so that's kind of a weird one. So here's a rational function. Okay, the domain of this function is all real numbers except for 2, because that's where there's an asymptote. So what that's saying, as long as you're not at something that's not in its domain, rational functions are continuous everywhere. Okay, so in this case, it's continuous everywhere, but at 2, because 2 is not in its domain. There's a vertical asymptote there. And this will make more sense when we start working these problems. Okay, now, if we have x to the 1 over n, that's continuous on all reals if n is odd, so that number is an odd number, and it's continuous from 0 to infinity if n is even. Whew, that seems really scary. No. Okay, there's an odd number, there's an even number. So if it's an odd number, like the cube root, you could take the cube root of anything you wanted. You could take the fifth root of anything you wanted. It doesn't matter if the x values are positive or negative. Okay, so here is what that graph looks like. So if it's an odd, it's continuous everywhere. If it was an even function, so a square root, a fourth root, a sixth root, you can only take the roots of 0 and above, positive numbers. Here's that graph. Okay, so they're telling you, here's where you can assume that if it's an even number, it includes 0 and it goes to infinity, and you know it's continuous. If it's odd number, if it's odd, you know it's continuous everywhere. Okay, sine and cosine function, they're continuous everywhere. Here's what we talked about yesterday, day before, that this is our exponential growth and decay functions. Well, they're continuous everywhere. There's no holes. There's a horizontal asymptote. That's not a problem. It's vertical asymptotes that are a problem. So you're guaranteed that. Okay, a log function. Remember we said for your log function, we want you to memorize that graph. So that's continuous everywhere. It does not include, not everywhere, everywhere greater than 0, and it does not include 0. So that's why they've got x is greater than 0. They say that b is greater than 0. You can never have a negative number in there. And it has to do with, it's like an oscillating function. It's really weird. We don't do those. We only use positive bases. Okay, and then inverse functions. So they're telling you, okay, say that you have some inverse functions. And remember from pre-calc and math 3 that we said, oh, okay, well, this function here, the domain of this function is the range of this function. The range of this function is the domain of this function. So this is good to know, because sometimes inverses are really hard to find. So or maybe not hard to find, the domain and range is hard to find. So here they're telling me, well, the range of this, well, the range of that is all values of y that are greater than 0. Okay, well, then the domain of its inverse function, where it will be continuous, is x is greater than 0. So you're looking at what is the range of a continuous function, and its inverse function will be continuous on that range, technically. Okay, so kind of think about how that works. Alrighty, now properties of continuity. Another thing that we can do, because we'll have all these functions mixed together, that if you know you have something that is a continuous function and it's multiplied by something, it's still continuous. If you add or subtract continuous functions, still continuous. If you multiply continuous functions, still continuous. If you divide, still continuous, as long as you don't get 0 in the denominator. And then a composition. So if something is continuous, if f is continuous at that point, then the composite function is going to be continuous. Okay, don't worry too much about this right here. We'll see this as we go along. We'll start talking about where we can assume that. Okay, so let's look at if we had to do a proof here. And it says for these numbers, justify. That means prove, show, however you want to say it, your findings using the 3-part definition. So we have to use the 3 parts because they told us to use the 3 parts. So sometimes you're going through and you're like, but I already know that it's not continuous because one of the things was violated. If they told you that you have to use all three parts, you gotta do it. Okay, so let's look at this one. When we start out, when C is -3. Okay, so let me just look. Okay, I already know that it's not continuous there. And remember, our rule said that the limit at this point has to equal the function at that point. I can see what the problem is, but I got to prove it. Okay, so when I find the limit of that point and I'm showing continuity, I have to show it from both sides. Okay, you can't just say, well, I know it is. Okay, so I'm going to say from the left. And I'm just going to call it f of x. So as I'm coming from the left, the function is approaching -1. As I'm coming from the right, the function is approaching -1. So the limit exists, right? Now, let's see, f of 3, that is equal to 2. Okay, so it's not continuous because f of 3 does not equal the limit as x approaches. Oops, I'm sorry, that should be negative. -3 does not equal the limit as x approaches -3. All right, let's look at c equals 3. Okay, so I'm just going to look at that right there. Oh, I know it's definitely not continuous. There's an asymptote here. So I already know f of 3 is undefined, and these don't exist, the limits coming from the left and the right. So I'm going to prove it, though. So here we go. The limit as x approaches 3 from the left of f of x. So as I'm coming from the left, I'm headed towards positive infinity. Does not exist. The limit as x approaches 3 from the right of f of x, coming from the right, headed towards positive infinity. Okay, I could say that the limit as x approaches 3 is positive infinity. Technically does not exist. And f of 3 is undefined. Now, I want you to be careful on this one because it's kind of tempting to go, well, that's sort of like does not exist, and that sort of does not exist. But remember one of those very subtle things in our rule, as we go back here, the limit had to exist. Okay, so that one's tempting because it's like they all sort of don't exist. No. So we're going to say not continuous because, again, when you're proving something or justifying, you have to give a conclusion. Not continuous because f of 3 does not equal the limit as x approaches 3 of f of x. And that one's kind of subtle, I know, with all that undefined business. Okay, let's look at as c equals 7. Okay, let's look at 7. What's happening there? Well, f of 7 exists, and it's a number. It's 3. As we're coming from the right, it's 3. But as we're coming from, as we're coming from the left, it's 3. Right? I've got to keep that right. As we're coming from the right, okay, so we know the limit does not exist. So I'm going to say the limit as x approaches 7 from the left is equal to 3. The limit as x approaches 7 from the right is equal to 6. So that tells me that the limit, sorry about that, that tells me that the limit does not exist. Okay, and f of 7 is equal to 3. So not continuous because f of 7 does not equal the limit as x approaches 7. Okay. All right. Let's look at here. So this time we don't have a graph. We have some equations. And we want to find the values where the function is discontinuous. And we're going to describe the type, infinite or removable. Justify your answer using the definition of continuity. Okay, so I got to be doing this whole limit thing. Okay, so what I want to know here is I want to have an idea of what this is. Well, this is a rational function. And I know that there is an asymptote at x equals 3. Okay, so I know there's an asymptote there. And then I'm not sure, does this thing go in this quadrant and this one? Or does it go here and here? So I could just put in a test point. What if x was 4? What if I was over here? Well, that would be at 1. Okay, so I know it goes like, ooh, I just made it like look like an L. It shouldn't look like an L. So I know it goes there. And it's going to go here. Okay, so if I just know what the graph looks like, I could tell what's happening. Okay, so I know that the limit as x approaches 3 from the left. Okay, so as I'm coming from the left, this is headed towards negative infinity. Okay, the limit as I approach 3 from the right, so I'm coming from the right, that equals positive infinity. So right there we know that the limit does not exist. And we know that f of 3 is undefined. I shouldn't say equals. Okay, so f is not continuous. And the reason is that f of 3 does not equal the limit as x approaches 3. Okay, now, what type is it? It's a non-removable, infinite discontinuity. And I'll just put kind of here that it's a vertical asymptote. Oh my gosh, I'm sorry, you guys. Okay, let's look at what is happening over here. Okay, so if we're looking at where is it discontinuous, well, I know that there's going to be a discontinuity at x equals negative 2. Now, I don't know, is it an asymptote or is it a hole? So I would need to factor this thing. So I'm going to factor it to 2x plus 3 times x plus 2 over x plus 2. So I can see that there is a hole in the graph. Okay, so I know I got to look at negative 2. That's where something interesting is going on. Okay, the limit as x approaches negative 2 from the left of g of x. Now, this is interesting. I don't necessarily, well, actually, we could come up with a graph, right? 2x plus 3, that's just 1, 2, 3, up 2 over 1. Okay, looks like that. Okay, so, and even that, I don't even need to know what the graph looks like. I can just do direct substitution at this point. Okay, at -2, that would be -4 plus 3. That equals -1. Okay, the limit as x approaches -2 from the right. So again, direct substitution. And I know that that works because I know that this is a line. Okay? Okay, g of -2. That is undefined because there's a hole at that point. Okay, so f is not continuous. Because g of -2 does not equal the limit as x approaches -2 of g of x. Okay, this is a removable point discontinuity. Okay, that's it.